Hello everyone. So in this video, we are going to see the electronic chip cooling analysis by using ANSYS Workbench. So let's get started. So you can read the question. An electronic chip generates 1 watt of heat. It must stay below 50 degrees centigrade to function properly. A heat sink is attached to help, or heat sink, or we can say fins, is attached to help with cooling. Airflow over the heat sink is at 1 meter per second. So these things are given. And our objective is to find out the chip's maximum temperature as well as what will be the temperature of the air leaving the heat sink. So these things, this is the question. So the things which are given to us is this is the chip and this is the fin. Chip has dimension 10 mm by 10 mm by 1 mm, and fins has a cross section of 1 mm by 10 mm. On this fins, the air is flowing with a velocity of 1 meter per second in this direction, and air temperature is 20 degrees centigrade. Heat generation is there inside this chip, and the heat is conducted to the fins, and after the fins it is convected to the surrounding. So this is the surrounding. So let's get started with this analysis on ANSYS Workbench. So in the ANSYS Workbench, we are going to do the analysis in Fluent. So I will drag that fluid flow Fluent. We'll draw the geometry by using the design modeler. So right click, go to the new design modeler geometry. Okay, so since the units are in terms of mm, so I will convert the units in mm and just a little bit zoom in. Then on the XY plane, first we'll try to draw the chip. I'll put the dimensions. So H1 is 10 mm, while this V2 is 1 mm. And I'll make it center. Then I'll extrude it. So in the Z direction, it is up to 10 mm. Okay, I forgot to select the geometry. I need to select the sketch one. Okay, and then I'll click on generate. So this is our chip. For the fins, we want to assign another material, so we'll create another sketch. And in this sketch, we'll draw the fins. We can draw the fins by many ways. I'm going to use the polyline. You can use your own method. Now I have roughly drawn the profile of this fins. Now I will constrain the lines as horizontal and vertical lines. Then I will add the distances like this height. Let us consider this height is 10 mm and the inner height is 9 mm. Likewise, do for all these vertical lines. Then the fin thickness is 1 mm. So I will consider this distances as 1 mm. So by calculating the distances will be 2 mm. So this my profile is created, and the profile should be closed profile. Then I will extrude this profile as well, this sketch as well. This is my sketch 2. I will consider the operation as add frozen so that I can assign different materials and the different solid will be created for this fins. The length is 10 mm in the Z direction. So I'll just generate it. So here you can see the two parts are there. One is for this chip and second is for the fins. So we can rename this so it will be easy to identify. So these solids we have created. Now over to this, the air is going to flow. So we need to create the outer environment as well. So for that, one command is there, that is enclosure. So that command I'm going to use. So just we need to put the appropriate distances like cushion on the plus x direction. So on the plus x direction, at what distance you need the cushion, at what distance you need the outer environment. These things you need to put respectively in the respective directions. So in positive x direction, I will add 10 mm. In positive y direction also, I will add 10 mm. Positive z direction, that is initial direction, so I will add little bit more, that is 15 mm. In negative x direction, I'll add 10 mm. In negative y direction, actually, it should be attached to the base. So, but here you can see the distance should be greater than 0. And we need to think about the meshing as well. So that's why I'll add 2 mm. And in the z direction, we need sufficient more distance to avoid the reverse backward flow. So I will add this as a 30 mm one. Okay. Then I'll generate it. It will consider as a frozen and it will create one more solid. So we can rename this to identify it quickly, rename it as fluid underscore air. So these solids we have created. So since we are dealing with solids and fluids, so we'll select all these things by pressing Control button and then right click on it and make a new part. Then we can close this. Then I'll go to the mesh. Okay, so the geometry is loaded. We can check the geometry once. So the solid chip is there, then fins are there, and this fluid air section is there. Then we need to ensure that there should not be any connections. So here we can see there are no connections. And the mesh we can generate auto mesh also directly by putting the element size as 2 mm because that is our least dimension. Or we can provide the separate dimension for the chip, for the fins, and for the outer structure as well. I have kept the element size as 2 mm and directly I will generate. So here we can see this is auto generated. So just once we want to see the mesh of this fin and chip. So I will hide this body. So we can see this is a little bit core structure. So what we will do, we will do the separate meshing of this chip, fins, and this outer structure. So I will erase this mesh. So right click on mesh and go to the clear generated data. And then I'll mesh it separately. So I'll select the chip, right click on it, go to the insert and go to the sizing. So body sizing method we are going to use. So one body we have selected, that is chip. Element size, put this element size as 0.25 mm. We are dealing with mm. And then we will generate the mesh on this selected body only. So I'll select this body, then right click, go to the generate mesh on selected bodies. Okay, similarly we'll do for this fin structure as well. So right click on this fin structure, go to the insert, sizing. Again the element size is 0.25 mm. Again I'm keeping the same. And generate the mesh on this, sorry, first select the body and then right click it. Generate the mesh on the selected body. Then for the outer body, just I'll show that outer body. We'll again use the same method. So select this outer body, right click, go to the insert, sizing, and the element size will use as 2 mm because that is the least dimension in our case. So again I'll generate the mesh. Okay, once again we'll see the mesh on outer side. It looks okay. Let's hide this outer body, and here it looks okay, no problem. Sorry. Okay, so now we'll create the different parts. So we'll consider this face as inlet from where the air is coming. So I'm going to select the faces. So this is my inlet face. So right click on it and create name selection. Inlet. While writing this name should be appropriate. So likewise, this is your outlet. Create name selection. Then this is wall structure. So from this side, the air is not going to leave, and the remaining faces are symmetry. We have created name for the faces. Now it's time for the bodies. So I'm selecting the bodies. So this is my outer body first. Right click on it, create name selection. This is my fluid structure. So I will write fluid underscore air. Again, I'll hide this body. Then right click on this fin structure, create name selection, solid underscore fin. Likewise for the chip also. Okay, we can see all these things, whatever we have done, that all these things we can see in this name selection tab. So just expand it. So this is inlet, this is outlet. Okay, then this is the wall bottom. These are the symmetrical faces. Then this is the fluid air body. Then solid fins are there, that is inside. We can hide it and we can see that also. Then solid chip structure is like this one. Okay, so all the things are recorded. So now we need to update it because we have given the names. So update it. And once we got this message, we can move ahead to the front. Okay. So I'm going to click on double precision and based on your course on your computers, we can select the solver processes, number of solver processes, and go to the start. Okay, so here we can see the general things like scale we can see, and that's okay. We can check the mesh. So it looks okay, but still we'll see the report quality. And we can see there is no warning message over here. So that means our mesh is good. Then we can display the things, we can change the units. Only one unit I will change, and that is for the temperature. So likewise, other units also you can change. So temperature by default it is in Kelvin. I will convert that into degree centigrade. Then we are going to use pressure-based solver. We are going to do for the steady state analysis, and gravity is not that much important in our case. So go to the models. In models, multi-phase is not there. Energy we need to turn on. And models we can use the SST K omega, K epsilon, or laminar also. I'll consider the laminar model, laminar viscous model. Then I'll close this models and open this materials. In material fluid structure, by default, air is there, and we are going to use only air as a fluid, so no need to add anything. But in solids, only aluminum is there by default. We need to add the copper as well. So double click on this aluminum. Go to the fluid database. Here, material type is fluid. Change it to the solids. So solid structures we can see. So this is solid material. So we'll copy that and close it. We can add as many as fluids and solids as we want. Then we'll close this materials and check the cell zone conditions. So in fluid region, by default, fluid underscore air is coming because we have given the appropriate name. So that's why I'm saying put the appropriate names. And in solids, so solid chip is there, solid fin is there. So in fluid air, we'll see fluid is air is assigned or not. So here we can see only one material, only one fluid is there, that is air. So no need to worry about it. In solids, we need to see. So for the chip material, by default, it is aluminum, but we need to change it to the copper. And solid is this solid chip is generating the heat. So we need to add this in terms of source term. So we'll turn on this source term. So here we can add that thing. So energy, number of energy sources are one, and we'll add that as a constant heat. So 1 watt heat we need to add, but we need to consider the volume of the chip also. So as we know, the chip volume is, as you know, the chip volume is 10 mm by 10 mm by 10 mm. So we need to do some calculations. So I'll open the calculator. So it's 1 watt divided by volume of the chip. So 1 watt divided by volume. Volume is 10 mm by 10 mm by 1 mm. So 10 mm, that is nothing but 0.01 into 0.01. So this is 10 mm by 10 mm into 0.001. So 10 mm by 10 mm by 1. So 1, then 5, 6, 7 zeros are there. 1, then 7 zeros. 1, 1, 2, 3, 4, 5, 6, 7. Then I'll click on OK. So source term and heat generation we have given. Then for the fin also we'll check whether aluminum is assigned or not. So for the fin, aluminum is assigned. So no worries. Then we'll go to the boundary conditions. We'll double click on this boundary conditions. So this is the inlet. By default, velocity inlet is given because we have given the name as inlet. Then we will add the boundary condition for the air as velocity is 1 meter per second, normal to the boundary, and its temperature is 20 degrees centigrade. So these things we have added. Then for the outlet, pressure outlet is there, symmetry condition is there, and for the wall bottom wall condition is there. Just to ensure that you can check, you can change by using this also. And we can do the hybrid initialization. So we'll do the hybrid initialization. Okay, so hybrid initialization is done. Then we'll go to the run calculations and we'll add the iterations as 400 iterations. Then press on calculate. Okay, the calculation is completed. So we can see this message also that solution is converged. It is converged in the 75th iteration. So we are ready to go for the to check the results. Okay, we'll see the flux reports once and then we'll go to the CFD post processing. So we'll go to the reports, fluxes, and here we'll see the mass flow rate. So we'll select all the things and we'll click on compute. So here we can see that the net result is nearly equal to the 0. If it is nearly equal to the 0, then we can say that our solution is correct. And likewise, we can see the total heat transfer also from the different regions. So this is the total heat transfer rate in the different regions in terms of watt. So we'll close it and we'll open the CFD post processing. Okay, so in post processing, first we will see the vectors. So location will see whether our flow is happening or not. That's why we are going to see the vectors. So at the inlet condition, the vectors are in this direction. That means flow is happening in this direction. Likewise, we will see at outlet condition also. So in the outlet also, the flow is happening in correct direction. So that means our flow direction is correct. Now we'll see the contours. Now for that, we'll add one plane also. So we'll add the plane which is parallel to YZ. So on this plane, we'll try to plot the temperature contours. So this is temperature distribution. So this is you can see at the middle of these two fins, and we can see maximum temperature is at the chip. We can change this unit also from Kelvin to degree centigrade, and we'll change the legend also. Okay, so we can see minimum temperature is nearly 20 and maximum temperature is 23.856. So as per our problem, we need to see the temperature on the chip, maximum temperature on the chip, and that should be below 50 degrees centigrade. So let's try to plot the temperature in the chip. So you can see the chip temperature is not changing that much, and it is around 43 to 44 degrees centigrade. So it is below 50 degrees centigrade. So that objective we have achieved. Then likewise, we can see the fin temperature also. So this is the fin temperature. Since the fin is made up of aluminum and there is a solid contact between the chip and fin. So that's why the temperature of fin is also nearly the same. Then we can see the temperature at the outlet. We want average outlet temperature, so that we can get by using this calculators. So in calculator, function calculator is there, and function is area average, location is at the outlet, and variable is temperature. So let's calculate. So average temperature at the outlet is 295.052 Kelvin. That is nearly, you can say, 22 to 23 degrees centigrade. Okay, so that's all from this video. Hit the like button,